Hello. In this video we're going to take a look at solving the time-independent Schrödinger equation in cases where we are scattering from a potential step. So this is a particular instance of solving the time-independent Schrödinger equation in a case with a constant potential. So let's write that down. So our potential is going to be set equal to V0, and the form of the equation then looks like this in one dimension. And the solutions to the equation in general take different forms depending on whether E, the energy of the particle, is greater than or less than V0, the constant potential in the problem. So first, the case that E is greater than V0, we have plane wave solutions. So they take this form in general, and you can check quite easily by substituting those into here that these will solve the Schrödinger equation for particular values of k, which we'll check in a second. The second case, again for E is greater than V0, but well, these correspond to travelling waves when we add in the time dependence in the way that we always can add back in the time dependence in terms of the constant, the phase winding. As a function of time. These are two travelling waves, but in certain cases, depending on the boundary conditions, it can instead be important to look at standing waves. Much like we can look at solutions to the wave equation for sound, say, we can have travelling waves of sound, but we can also have standing waves of sound when trapped between two walls, for example. So in another case, for E is greater than V0, we can have so let's just write this down. These are travelling waves or plane waves. And we can also have standing waves. Where, of course, you can, in fact, make this form of solution in terms of causes and sines from this solution in terms of exponentials, but this is going to be a particularly convenient form to consider in those cases where standing waves are the relevant things to consider. Let me just magic my globe away for a second with a quick slap of this board. Good, so let's write down that these are standing waves. Good. Now in the case where E is less than V0, the solutions are going to be exponentially decaying instead of being either travelling or standing. So they take the following form, where kappa here has taken the place of k, and this is so that both k in this case and k in this case and kappa in this case are real numbers. So this looks like it doesn't have an analogue in terms of classical waves. We have both of these in terms of like sound and light. This looks like there shouldn't be an analogue to just something like a wave that just exponentially grows or decreases. But actually they do exist classically, and they're what's called evanescent waves. Or you might prefer to call them evanescent solutions to the equation because they're rather strange to try and think of them as waves. I'll give you some examples of those in a classical context. So these are the general types of solution we're going to be looking for depending on how our energy relates to our potential. So let's set up a particular problem of interest, which is scattering from a potential step. So we'll clear this off and specify the problem.